Hey everyone, in this video I wanted to talk about an overview of limit techniques. At the end of chapter 2 you'll have a lot of different limit techniques under your belt, but you may have some trouble deciding when to use which one or what type of limit you're looking at. And this is kind of the overview that I use when I apply it to limit problems. So hopefully it's useful to you. The first thing I always try, step 1, is to try to plug the value in. If you're taking the limit as x approaches a number like a, if your function's continuous at a, then you can just plug a into the function, find f of a, and that's usually your limit. If you can't plug it in, like if it's discontinuous there, if you end up with a 0 in the denominator, then in step 2 you have 3 different things you can try in order to get rid of that discontinuity or cancel out the piece that is giving you the 0 in the denominator. You should try factoring. If you have square roots, you can try multiplying by conjugates. And if you have fractions, you can try to get a common denominator and then do some kind of factoring and canceling. Now if you can't do that and you still have this discontinuity in the denominator, typically that means you have a vertical asymptote at that place. And then you just have to analyze it and figure out what happens to your function on either side of the vertical asymptote. So you take the limit as x approaches a from the left and the limit as x approaches a from the right, and you try to figure out if you get positive or negative infinity. In step 4, the last thing is rules for limits at infinity. So if you're taking the limit as x approaches infinity, these are a little bit different from the other kind of problems here, but I'll have some separate rules for dealing with that at the end as well. So I have some examples illustrating each of these coming right up. Alright, so the first thing, like I said, is if you're taking the limit as x approaches a number, try to plug that number in. For this first example, as x approaches 1, this function, nothing bad happens in this function. So the numerator, you get 1 cubed, which is 1, minus 7 times 1, which is 7, and plus 12 times 1, which is 12. And the bottom, you get 4 minus 1, which is 3. So you crunch these numbers, I think you get 6 over 3, which is 2. And that's the value of the limit, right? Because this function happens to be continuous at 1, so you can just plug it into the function. So always try that first. If that doesn't work, then you go on to other things. Like in this next example, same function, but if you take the limit as x approaches 4, you have that 4 minus x in the denominator, which will become 0, and then that won't work. So the next thing you try is factoring, and this is definitely something that I think can be factored. In the numerator, we'll factor out a greatest common factor. Don't forget that should be your first step, always, of factoring. So everything has an x in common, so we're going to pull out an x. I'm also going to factor out a negative in the denominator because typically you see the factors as x minus 4 rather than 4 minus x. So we'll probably factor the numerator and get an x minus 4 that can be canceled. Also, I should have my limit as x approaches 4 right here. Let's try that again. So limit as x approaches 4. Now we can factor the numerator again. It's a trinomial. If you take two numbers that multiply to 12 but add to negative 7, I believe that should be x minus 4. Minus 4 is one of those numbers, and minus 3, so x minus 3. Right, so that's how that trinomial factors, and now you can see the x minus 4s will cancel. So what do we have left? We have the limit as x approaches 4, x times x minus 3, and on the bottom we just have a negative 1. And now we can plug in 4 because nothing bad happens to our function when we plug in 4. 4 minus 3 is 1, 1 times 4, so we'll have 4 on top and negative 1 on bottom. That gives us negative 4 as the limit. In this next limit, we can't plug in 3 because it makes the denominator 0, and we have a square root in the numerator, and often this means you need to try multiplying by the conjugate. The conjugate of the square root of 3x plus 16 minus 5 would be the square root of 3x plus 16 plus 5. All you do is you change the minus to plus or the plus to minus. Nice things happen when you multiply expressions by their conjugates. When we FOIL this out, there should be no more square roots left over, and hopefully we can cancel out an x minus 3 and then go on with our limit. So let's see what happens when you FOIL this out. First you have the root times itself, and when you multiply a square root by itself, you're squaring the square root. You just get whatever was underneath the square root. So that's the root squared. Now notice, if you take the root and you FOIL it, multiply by the 5, you'll get 5 times the root. And then you take these two pieces and multiply them, you get negative 5 times the root. So the inner and the outer pieces here cancel out. So we can actually jump to the last piece, which is negative 5 times 5, which is minus 25. So notice, like I said, this is where the roots will completely cancel out. Now let's just simplify this numerator off to the side real quick. We'll have 3x, and then if we take the 16 minus 25, we get minus 9. And then if you factor out a 3, you get 3 times x minus 3. So right here, that's what we actually have. And as you can see, that's where our x minus 3's cancel. So what we're left with, limit, as x approaches 3, is 3 over, and then we have the conjugate basically, the 3x plus 16 plus 5. Now when x goes to 3, the numerator approaches 3, and the denominator, we have 3 times 3, which is 9, 9 plus 16, which is 25, square root of 25 is 5, and then 5 plus 5 gives us 10. And that's our limit. In this example, we can't plug in h equals 0 because our denominator would be 0. And there's no conjugates or obvious factoring we can do, but we do have two fractions, so we can try to get a common denominator and write it as a single fraction. Our common denominator will be the product of these two denominators. I'll write it as 5 times 5 plus h. So this fraction will need a 5 on top and bottom. This fraction will need a 5 plus h on top and bottom. So this will look like 5 over our common denominator, 5 times 5 plus h. And then minus, this will look like 5 plus h over our common denominator. It's a weird 5, but you get the idea. Okay, in the next step we'll write them together. So on our numerator here we'll have 5 minus h. Real quick, just to clarify that, you have to make sure this minus goes to both of these pieces. So I'm actually distributing minus 5 and a minus h. That's all I got here. And this is all over our common denominator, which is 5 times 5 plus h, which is all over h. Okay, so we have 5 minus 5 on the top, and so we'll have a minus h left over. And I'm going to write this as two fractions now. So minus h over 5 times 5 plus h. But if you treat this h back here, this one right here, if you treat this like a fraction, h over 1, what we're going to do is we're going to split that out, we're going to flip it and multiply it, so it'll actually be 1 over h. Right, so really, once we get a common denominator here, we're writing the denominator as a fraction. So we have a fraction divided by a fraction, and the way we divide fractions is we multiply by the reciprocal. So I'm taking this piece, flipping it, and multiplying it. And the reason I want to do that is you can see my h's are going to cancel. So in this next step, make some room here, we have the limit as h goes to 0. We will have a negative 1 on top, and we're just left with the 5 times 5 plus h on the bottom. Okay, now we can plug in the h equals 0. That will give us negative 1 over 5 times 5, or negative 1/25. And that's our answer. For these examples, we've basically exhausted our options on canceling out the 0 in the denominator, and we know we're going to have an asymptote. We just have to figure out what type of asymptote. So this function, as x approaches 2, the denominator will approach 0, so positive or negative infinity will happen. But we want to figure out which version, right, positive or negative. So we're basically just going to look at what the numerator and denominator approach. The numerator is not changing, so as x goes to 2 from the right, the numerator approaches 1. The denominator, on the other hand, as x approaches 2, the denominator is approaching 0, but think about the values that we're plugging in. If we're approaching 2 from the right, we're plugging in things like 2.1, 2.01, 2.001, very close to 2, but above 2. So when we subtract the 2.1 or 2.001 minus 2, we're going to get something positive, but very, very small. So I'm going to denote this with a positive 0. Now that's not proper math notation. There is no such thing as a positive 0. This is just my notation for a positive number that's very, very small, very close to 0. And this is important because if you have something that is positive and fixed, like 1, and you divide it by something that's positive and infinitely small or infinitely close to 0, you will actually get positive infinity. Right, if you take a fraction, if you take your calculator and take 1 and divide it by 0.1, 0.01, 0.001, you will get larger and larger numbers. So that's what this notation says. You have a fixed value 1 divided by something small and positive, so the overall fraction will become infinity. On the other side, as x approaches 2 from the left, top is still going to 1. The bottom this time, though, we're plugging in numbers like 1.9, 1.99, 1.999. When you subtract 2 from that, you're going to get something that's negative, and very, very small. Positive over negative is negative, so this will approach negative infinity. And then for our last limit here, in general, notice we have two different things from the left and right, but even still, even if they were both positive infinity, this is a special case of the limit not existing. The limit does not exist if it becomes infinite or negative infinity, because the limit has to be a specific number that we're approaching. So for part C, we would just say the limit does not exist. Okay, so let's do the same thing one more time down here. The numerator for this first one is going to be approaching 4 minus 5, which is negative 1. The denominator, we're plugging in numbers like 4.1, 4.01, so we subtract, we get something that's positive and very small. Notice we square it afterwards, right? So we're getting something that's positive and small, but then we're squaring it, and it's still going to be positive and small. So we get negative infinity because we have a negative over a positive. For part B, the numerator is still approaching negative 1. As x approaches 4 from the left, we're plugging in numbers like 3.9, 3.99, 3.999. When you subtract 4 from that, you get something that's negative and small, but you still have to square it. So negative and small squared is actually going to become positive and small. So this will still be negative infinity. It's a bad infinity. There we go. And then for this last one, just like last time, even though they're both going to negative infinity, this is still a case of the limit not existing. Right? We're just being more specific than not existing. We're saying the limit doesn't exist, and in fact, the values blow up to negative infinity around 4. For infinite limits, the first thing to think about is the highest power of x is going to grow much faster than all the other powers of x. So for this example here, as x goes to negative infinity, x to the 7th will grow so fast that it will dwarf out anything that happens with the x squared. So what we usually write is the limit as x approaches negative infinity of this function is the same thing as the limit of just the leading term, right? Because that piece is going to basically overtake the entire function. So what is going to happen to this piece as x becomes very large and negative? X to the 7th, 7 is an odd power, so as x gets very large and negative, x to the 7th will get very large and negative. And then when you multiply that by 3, you just get negative large times 3, which is still large and negative. So we would say that this limit equals negative infinity. Right? The values are getting more and more negative, and as x goes to negative infinity. Now, that's a single polynomial, so all polynomials go to positive or negative infinity at infinite limits. If you have a rational function, though, you could end up with 0, you could end up with infinity, or you could end up with a number, like a horizontal asymptote. The general steps for calculating the limit at infinity of a rational function is that you take the highest power of x in the denominator and divide everything by that power. So in our case, our denominator is this, and our highest power of x is x to the 4th. So we're going to take every single term here and divide it by x to the 4th. If you do that, you get this, everything over x to the 4th. And now you can do some canceling. X cubed over x to the 4th gives you 9 over x. This reduces to 1 over x squared. This stays the same. These x's cancel, so you just get 3 here. And this reduces to 4 over x squared. Now what happens when x goes to infinity, think about something like 9 over x. If you plug in a very, very large number for x and you take 9 divided by that number, you're going to get a pretty small number, a number close to 0. And if you take an even larger number, even bigger than the last one, and you take 9 divided by that, you're going to get even closer to 0. So it turns out if you have something fixed and you're dividing it over something infinitely large, and in fact this wouldn't matter if it was positive or negative infinity, because this would still be very, very large, something fixed over something very, very large will approach 0. Right? The larger the denominator gets, the closer to 0 your fraction gets. So this piece of the fraction will go to 0. For the same reasoning, this one will go to 0, and this one will also go to 0. Fixed on top, growing to infinity on bottom. And this one as well, fixed on top, growing. So the whole numerator is approaching 0, and the whole denominator is approaching 3 plus 0, which is 3. So overall, our limit will be 0. So if you look at the graph of this function, as x goes to infinity, our values should get closer and closer to 0 as you go off to the right. And lastly, one note on these limits at infinity. Sometimes you have square roots in there and you have to be a little bit tricky about what your highest power of x is. So like here in our denominator, we have x squared here, but we also have an x to the 4th underneath the square root. Because it's underneath the square root though, the square root of x to the fourth, which is x squared, is actually the power of x that we have right here. Right? You have to adjust your power of x based on the root that it's underneath. So square root of x squared is x squared, so it's tied with this one. The highest power in the denominator will be x squared. So we're actually going to divide everything by x squared. And again, when we divide underneath the root though, if you take an x squared and you put it inside a square root, it becomes an x to the fourth to balance it out. So we're just saying that the highest power is actually x squared, because square root of x to the fourth is x squared. And then when we divide it inside here, x squared inside a square root is actually x to the fourth. So it's kind of weird, you have to adjust. See how we're doing x squared here, but x to the fourth underneath the root. It's actually equivalent, but we're just adjusting for the radical. So we're dividing everything by x squared. And then in the next step, they cancel out here, we get 6. They cancel out here, we get 4. They cancel out here, we get 16. This is the only piece with x's left over, 1 over x squared. And just like in the last example, as x goes to infinity, 1 over x squared will go to 0. Something fixed over something infinitely large will go to 0. So we really have 6 over 4 plus square root of 16. Square root of 16 is 4, so we really have 6 over 4 plus 4, which is 8. Which if you divide top and bottom by 2, you should get 3/4 as your final answer. Alright, so hopefully this has been helpful. Let me know if you have any questions, and thanks for watching.